Okay, this is on in behavior models and asymptotes, and today we're going to spend more than one day on this, and today we're going to spend the time on in behavior models, okay, and then we'll do in behavior asymptotes the next time. Okay, so first I want to go through the definition of what they call an in behavior model, and then I'll go through an example, okay. So by definition, the function g of x is an in behavior model of the function f of x if, okay, one of these has to be true. The first one, the limit of, up in the numerator is f of x divided by g of x. Now this time, instead of approaching 0, the limit's going to approach, x is going to approach positive or negative infinity. Okay? Okay, the limit of f of x divided by g of x as x, that means as x gets really large, x is going out to infinity both ways. If that limit is 1, okay, when g of x does not equal 0 and the absolute value of x is large. And we're actually going to do an example and do that on a table. Okay?
Yeah, this has large.
It goes to infinity. It'll get really big. Yep. Okay. And then you need an or, and I would highlight that. Okay? Or the limit of f of x as x approaches positive or negative infinity equals, when that limit is 0, when the g of x function equals 0. Okay. Now, I'm going to do this by an example. Let's say I ask you to graph in y sub 1. We're going to graph 2x to the third minus 7x squared minus 8x plus 16. Okay, and this is like our f of x. This is our f of x. Okay. In y sub 2, I want you to graph the largest term that's in f of x. So we're going to graph 2x cubed. Okay? We're going to graph that 2x cubed. And that's like our g of x. Okay? And then it says up here that we need to divide them. So in y sub 3, we want to divide them. So my f of x is in y sub 1. And my g of x is in y sub 2, so I need to divide them. Okay? The bars key, yep. Okay? Okay, and let's go ahead and put those in. The other thing, check your mode. Make sure you're back in connected mode. You can clear anything out of the equations, but check your mode. Make sure you're back. All the first ones are highlighted. Question. Okay, and then put in 2x to the third minus 7x squared plus 8x. It's allergy time. Okay, and then in y sub 2, put in 2x to the third. Okay, and then in y sub 3, put in, you got to use the vars key, right arrow over to y variables, okay, and then you're at function, and pick up y sub 1. Okay, and then divided by, then use the vars key, right arrow over to y variables function, and go down and pick up y sub 2. Okay, now, I'm going to do this by looking at a table, okay, because it says if this limit goes to 1, okay, then it is an end behavior model. So, do second function table set, and we're going to, might want to write this down. On the second function table set, we are actually going to do the table start. We're going to start at 0, but I want the x to get really large, okay? So I'm going to do the delta table, and I'm going to go by 100. So, and auto is okay, okay? And that table set's right above the window key, okay? Okay, and then go in and look at your table, and that's right above the graph key. Now, I don't care what the x. Ooh, I didn't start it right. Sorry, I didn't start at 0. Look at my table then. Okay, so you can see the x is going 0 to 100 to 200 to 300. And I don't care about the y sub 1, the y sub 2. What I really want is that y sub 3. Is this y sub 3 getting closer and closer to 1? Yeah, it's approaching that as a limit. Okay? So, that is telling you that this is an end behavior model of the original. Okay? Shortcut, it's the highest term, is the end behavior model. Okay? You ought to be able to look at this and say, this is the end behavior model. It's the highest term. Because we just did it on the table and just showed that that approaches 1. So it fits this part of the definition as x gets really large. All right? Can you see this is getting closer and closer to 1?
Right.
Yep. So it's approaching that as a limit. Okay? Okay? Think about it a little bit. Okay. Now, they also give you a theorem. Okay? Okay? Theorem 11 says if f of x, and they write it out in a polynomial form, f of x equals a sub n x to the n power plus a sub n minus 1 x to the n minus 1 plus, and show 3 dots to show that we left out several terms. And then you need a plus sign on both ends of that when you leave something out. And then a sub 1 x, and then plus a sub 0. Okay, and in this a sub n cannot equal 0. Then y equals a sub n x to the n is an end behavior model of f of x. So another way, if you look back up at ours, this is our, if you look here, this is our beginning polynomial, and it's telling you that first term is the end behavior model. So y equals 2x cubed is the end behavior model. Okay? Okay, there are only 4 types of end behavior models. Okay? For n greater than or equal to 1. And most of these you already know. Okay? They just haven't called them end behavior models yet. For n greater than or equal to 1, there are only 4 types of, and they call them polynomial end behavior models. Okay. You spend a lot of time on the first two in Algebra 2. Okay. If n is even, I'll say it another way. If n is even, like 2, 4, 6, 8, and your a sub n, if it is greater than 0, okay, you're going to get a graph that opens up. Because it's going to be like y equals x squared, y equals x to the 4th, y equals x to the 6th. It's going to be something like this. That's just a rough sketch. If it's x to the 4th, it's actually going to open up a little flatter down here at the bottom. And you can try it on your calculator if you just go in and graph y equals x squared, y equals x to the 4th. Okay? And this was, if the a value was positive, that's like if I did y equals 5x squared, something like that. If that's positive, it tells you it's going to open up. Should have gotten that in Algebra 2. If n is even, okay, and the a sub n is less than 0, how is it going to open? It's going to open down, so it'll be something like this. If it was, and it doesn't mean it doesn't say it has to go through 0. It's just it's going to open down. And same thing if it's like a negative 7x to the 4th, it's going to open down. Okay. Okay. If n is odd, like y equals x cubed, y equals x to the 5th. Okay. If the a sub n is positive, okay, and most of these you already know, if it's positive, it's going to open like this. Y equals x cubed, okay? And then if your n is odd, and it could be x to the 5th, x to the 7th, x to the 9th, and if your first coefficient, if the biggest coefficient is less than 0, okay, then your graph's going to do this. Going to open this way. Okay, and basically those are the 4 types of polynomial end behavior models. Okay, okay. I'm going to look at another graph. Okay, another example. Say I ask you to graph in y sub 1 the polynomial is a negative 5x to the 4th plus 5x to the 3rd minus 10x plus 1. Okay, now, before you ever start graphing that and looking at your window, part of the reason they're covering this is so that you know whether or not you're seeing the whole graph. Okay? This is a x to the 4th. Okay, so it ought to be looking like this. Okay, opening, and it's negative, so it ought to be opening down. Right? Okay. In what is the end behavior model? First term. Yep, first term. So y sub 2 is a negative 5. Oh, you guys, add one more thing. This should have a decimal point on it. Sorry, left the decimal off. But that's still the first term is the end behavior model. Okay? In y sub 3, I still want you to put in, and if you already have it in on your calculator, just leave it there. Y sub 2 divided by, or y sub 1 divided by y sub 2. Okay? Now, I'm going to give you a specific window. I don't want you to graph the whole thing until you do this window. For the x, I want you to put in negative 8 and 8. And the scale, I really don't care about the tick marks on this one. So if you want to turn off the tick marks, put 0 in. Right? In the y, I want you to put in negative 10 to 10. Same thing, I don't care about the tick marks. Okay? So all I want you to do is put in the first equation, put in a negative 0.5 x to the 4th plus 5x to the 3rd minus 10x and plus 1. The second one, put in a negative 0.5 x to the fourth, and then I want you to do that window. Go negative 8 for the x min, 8 for the x max, and turn the tick marks off to 0. And then negative 10 to 10, and turn those tick marks off, go to 0. Okay, and on this one, go ahead and graph. Oop, my axis is off. If your axis is off, turn it back on. Let's just look at the first one. Turn the others off. Look just at the first one. Okay. Now, here's why the author is even covering in behavior models. Why even talk about it? If you look at that graph and look at the window, I specifically gave you a window so that graph actually looks like what type of graph? It actually looks like an odd one. Okay. So if you know what the models look like, you know you're not seeing the whole graph. Okay. Because your graph ought to be coming back down. Okay, it ought to be looking like this. Okay, go ahead and turn on the second one. Okay, don't have the third one on yet. Okay, turn on the second one. Okay, graph. Do you see any of that second one show up? Yep. Okay. It looks like those two aren't anything in the same family of graphs. Okay, but that second one is the end behavior model. Now, here's how you show it. Okay, go to second function format, or sorry, it's above zoom. Sorry, it's just zoom. Go to zoom. Okay, and now right arrow over to memory. And it's because of this that I'm going to have you change your zoom set factors. Okay. Right arrow over to memory and go down to zoom set factors. If I would put a 2 in for the x, 2 to the fourth power would be 16, right? So as the x is changing by 2, the y is changing by 16. So to get that to work, what you do is you go down to set factors, okay? By default, your calculator is probably, and some people may have changed it, but by default it's x set factor 4 and y set factor 4. Okay, but if I put in a 2, then the y is going to go to 16. Okay, do that, change those. So we're doing 2 and 16. If this would have been a 3, what would this have been? An 8. Okay, because 2 to the third power is 8. If that would have been to the fifth power, it would have gone to 32. What? Yes. Yeah, it'll mess it up. Yep. So, like once we get done with this, then you'd set it back to 4 and 4 or 2 and 2. I would go back to the default. 4 and 4. Yep. Okay, go back to the graph. Okay. Now, to show that these two graphs are in the same family and one's an end behavior model of the other one, okay, do a zoom out. Okay, zoom out. Now, when you come back to the window, nothing happens. Press enter. And you're still in zoom out. You're going to have to zoom out a few times. See, now you start seeing it come back down. Okay, the first graph's doing this, and it's coming back down. You're still in the zoom out mode, press enter again. Okay, they're starting to look closer. Press out, just press enter again. Oh. And they start approaching each other. Okay. Yep. So you can tell that second one is the end behavior model of the first one. Okay. So somewhere make a note. We did the zoom set factors, and what's controlling that is this exponent. I always use 2 here for the x factor, and then whatever that is, if that's a 4, 2 to the fourth would be 16. That's the y factor. If it was 2 to the 5th, then I'd go 32, okay? And then what did we do? We did a zoom out several times. Once you do the zoom out once, you're still in that mode, so you just press enter, press enter, press enter, press enter. Make enough notes there that it says you zoom out several times, okay? So that is another way to show that this y equals this is the end behavior model of the original. You could go in, let's look at the table, okay? Do second function table set, start at 0, count by 100, and look at your table. What I want to do is I want to go over to y sub 3. Oh, I turned it off. You got to turn it back on, sorry. You got to turn it on for it to show up in the table. Okay, go over to y sub 3, and you should see this. The decimals get closer and closer. They approach 1 as a limit. Okay? Okay. Any questions on that one?
My graph isn't shiny. Look at there, but it's not shiny.
Okay, on this next part, we've talked about drawing complete graphs. Okay? They'll give you directions that say draw a complete graph. And you've got to remember what that means. A complete graph means all the x and y intercepts, all the max and min points. Okay? You've got to see everything. Okay? Of y equals x to the third minus 2x squared plus x minus 30. Okay? Okay. On this one, I'm going to give you a specific window. Okay, on the window, do x. I want you to do negative 20 to 20, and I don't care about the tick marks for right now. And the y, I want you to do 80, negative 80 to 80, and scale 0. And for our zoom set factors, for zoom set factors, we're going to do x is 2, and y is the x factor is 2, and the y would be 2 to the third. It's all controlled by this. 2 to the third would be 8. Okay? Okay, so put in, you can go ahead and delete all the equations. Okay, and let's put in the y equals x to the third minus 2x squared plus x minus 30. Change the window to negative 20 to 20, set 0, and y min negative 80 to 80, scale 0. Okay, and graph that. Okay. Do a little sketch of this. You're seeing something like that on your graph, right? Okay, now, what the author will say is that a complete graph? If you put that graph on your paper, okay, is that a complete graph? What do you have to show?
X and Y intercepts.
And I'm showing the x and y intercepts. And what else? Max and min. Okay, so as far as the complete graph, okay, you've got to show all the x and y intercepts, which I'm showing those. All the max and min points. Here's the part that you got to be real suspicious, right here. Am I showing you the max and min points right there? You can't tell, okay? So first thing I want to do is I want to store this graph, because if I want to get back to it, I want to store it. So I just do zoom, right arrow over to memory, and do a zoom store. That just stores it in the temporary, like it's putting it on the clipboard. Okay? Okay? So you've got it stored. Okay, now what I want to do is I want to get in on that point and see if I'm showing the whole graph. Okay, so I'm going to do a zoom box. You could do a zoom in, but I want to do a zoom box. So do zoom box. When you do a zoom box, you're basically going to locate the upper left corner of your box and press enter. And then you're going to locate the lower right portion of your box and press enter. So you got a cursor here. I want to zoom in on this part. Put a pin down. Use your right arrow. Go down. I want a box around this. Put a pin down. Press enter. Okay. Still not very good. So let's do another. I want to do another zoom box. And I might not even have to go back to that. It might already stay in that zoom box. Okay, put a pin down. Use your right arrow. What's that? Press enter. Yeah. Okay.
So, just,
I think I'm still in zoom box. So I should just be able to go over and put a pin down.
so just over that portion where.
Yep, I want to see what's happening in there. You could do it by zoom in, zoom in, zoom in. You could do it that way too. But this way I stay in the area that I want to be in. Okay, now, can you see there are specific max and min points in that area? Yeah. So this graph, you basically need to write a little note here. You need to be very suspicious.
Which one is? So these are maximum points.
Yeah. Okay. So, and this is what this graph would be considered the local area. Okay. So let's do another graph of just the local area. So the local area is down here, and it would cross. There is a definite max. There is a definite min, and then up. Okay. So you would be able to find, and I could do second. Do you guys remember how to do max and mins?
Yeah.
Okay, let's do second function calculate max. Get it to the left of where it's crossing. And press enter. And it'll put that little triangle. And then get it to the right of where it's crossing, use your right arrow. And press enter. And guess, just press enter. Okay, so I have a max. This point, and if they ask you for your max and the min on the homework, you're going to go to 3 decimal places. So I have it at, and you look at the 4th decimal place, so it's just going to round to 0.333. And my y is negative 29.852. So, yeah. I did second function calculate. Do you guys agree with mine?
Yeah.
Okay. And do max. Okay, now you need to do this one. You do second function calculate and do the minimum. Okay? And that one, I'll let you figure. Okay? And this whole thing is called the local area graph. Okay? And we did zoom box on that. Okay? Okay, I want to give you one more example. What number was that? This same directions. Draw a complete graph. Of y equals 2x to the third minus x squared minus 14x minus 12. Okay, and I'm going to give you a specific window. X, so the x min is negative 10, x max is 10, and 0 for your scale. For your y, I'm going to go negative 40 to 40 and scale 0. Are our zoom set factors okay? 2 and 8, right? So they're okay. Okay, so let's input our new equation. Y equals 2x to the third minus x squared minus 14x minus 12. Take a minute, double check your equation. Okay, and then let's put in the window. Negative 10 for the x min, 10, scale 0, negative 40, 40, scale 0, graph it. Okay. If I graph that on my paper, okay, this is what I would graph. And by rights, there should be arrows at both ends. It's going to go. Am I showing a complete graph? All the max and min points, all the x and y intercepts. Be very, very suspicious. Which part?
Oh, where's the most attention?
Be very, very suspicious. Okay? So, do zoom, box. Or you could do, let's do zoom in. Let's do zoom in this time. Get over close to that. Press enter.
So why do we have these discussions?
Because you have to show a complete graph.
Okay.
And if you graphed it like that on your paper, you're not showing me the complete graph. The complete graph means all the x and y intercepts and all the max and min points. Are you seeing all the x intercepts?
No.
Okay. Just press enter again. Oh, there it goes. Okay, there's your local area. So you actually are not seeing the whole graph. Okay, this graph does this. Okay, so here's the intercepts. Okay, and remember, you can find the x-intercepts by doing second function calculate 0. Get it to the left of where it's crossing. Like if I wanted to find this, I'd get it to the left of where it crosses, get it to the right of where it crosses, and then guess, just press enter. If I wanted to find this one, to the left of where it crosses would actually be above, to the right of where it crosses. To get this one, you do second function calculate value at x equals 0. Okay? But be very, very suspicious when they say show a complete graph. Okay? Okay? That's what the author calls hidden behavior in your graph. Okay? And I forced the hidden behavior by giving you a specific window. Okay? Now, do me a favor, change your zoom set factors back to 4 and 4, and then as you work the problems, you change it to what you need. Okay? Okay, and that's the first day of notes on 2-4.